My research area is in the general area of nanoscience and nanotechnology, applied to thermal management, heat transfer, energy conversion, and surface nanomanufacturing. Now, the reason why I'm in this field, well, it's a long story. First, the reason why I'm in mechanical engineering. Well, the reason why I went to science is because most of the people in my generation go to science because they are good in math or in sciences, in physics or chemistry. It's not, there's no reason why we go there. It's just because we're good at it. You know, there was people didn't tell us, okay, what are you going to be doing as a scientist or engineer? But we were good at it, so we go to science. Everybody tells us to go to science. So I went to high school focusing in sciences, and I went to college afterwards, majoring in mechanical engineering because I thought it was one of the major that allowed me to do a lot of physics. And it's one of those fields that you could learn a lot of things. You know, mechanical engineering, for example, has fluid mechanics. You know, you could work in aerodynamics. You could work in material science. So on. So that's the reason why I was really interested in mechanical engineering. Now, when I was done with my master's degrees in mechanical engineering, I had to choose. Now I became more mature. I could, what do I really want to do? So I had a couple of options, and I decided to go into the field of nanoscience and nanotechnology because I learned that to really understand something, you need to go to the basics of it, right? So it turns out that nanoscience and nanotechnology really answers most of the questions that we have in the macro scale. If you want to know why, you have aerodynamics, or if you want to know why the water flow in a certain manner, or if you want to know why something tastes a certain way, by understanding the nanostructures or the nanomaterial that's made it out, that it is made out of, then you'll be able to answer this question. So it's more of a curiosity, being able to have a very good understanding of the world around us, and that's why I went to the field of nanosystems and microsystems. So what I'm working on right now, I lead the research lab at the University of Nebraska, and our lab is called the Nano and Microsystem Research Lab. We work in the general area of energy conversion using solid-state methods such as thermophotovoltaics and thermoelectrics. Also, we work on thermal management of high heat flux microelectronics, and what I mean by that is we're trying to find out how to cool electronics. And the conventional way of doing it in general is just to put a heat sink on top of your microchip, and then you use flow or some other liquid to cool it. And in my lab, what we're trying to do is to understand where the heat comes from and how do we solve that problem within the microsystem itself. So that means we need to design heat sinks, microcoolers that are on the same scale as the microprocessors. So that requires a lot of physics. Beside the engineering application, there's also the basic knowledge that we get out of it too, because it turns out when you go to micro nano scale, the physics that we learn in the macro scale, when you're in high school or in early college, it's not true. It doesn't apply anymore. So we need to now really start to learn new physics and try to understand and develop new concepts and theories. So those are the two areas that I work on. And recently, not actually recent, but in the past 4 years, we've been working on developing what's called the thermal logic devices and thermal rectifiers. And this topic comes about a problem that was posed to me by a colleague of mine at JPL, at NASA JPL. They're interested in exploring Venus. However, the temperature of the Venus is relatively high. It's about 400 degrees C. The pressure is very high, and there are radiation and other factors that makes it very difficult to explore. In order to explore any planet, one needs to have recording mechanisms, something you could use to record, or sensors, and those typically are based on electronics. And as we know today, electronics do not work at those high temperatures. So we had to come up with another solution. So the problem was, posed. And a lot of researchers were working on finding new materials that could sustain high temperatures. Others are looking for ways to avoid electronic at all. So in my group, we decided to take a totally different approach, which is to use heat itself. And the reason is because we were already familiar with heat. We do a lot of work in heat transfer, thermal management. So we thought, okay, if heat is just flow of electrons, flow of photons, flow of photons, which is just energy carriers, which is the same as electricity, then why can't we use heat itself to do computing? Okay, so we start working on this project. At the beginning we start looking at the theory, trying to find ways we could control heat, which is quite difficult. But at the end of the day, we were able to develop what's called the thermal memory device, a memory device that works entirely on heat. The 1 and 0s are actually high and low temperatures, and it works perfectly. And the next step was, okay, we need to actually make a prototype for that. And so we spent a couple more years working on it. And in this case, we specifically focused on what's called thermal rectifier. So we could rectify heat. We could change the direction of heat, which is not generally intuitive, but we thought we could do it, and we were able to do it, in fact. So we come up with the theory behind it, the model, we did it, and then we actually went and fabricate the device. All this is done at the micro scale because the underlying technology works only at that scale. which is when separation distance between terminals that we're interested in are below 1 micron. So these are some of the projects we work on. I have a couple of other students who work on energy storage, which is a big problem. In fact, it says that if you could store heat, then you solve a lot of problems. And one particular example is solar energy that we get every day. And one of the challenges is that at night we can't get the solar energy anymore, so we have to find ways to store it, right? And the current state of the art tools that we're using to store energy are not very well. They do not work as good as we would like them to work. And it's generally because they have relatively low thermal conductivity. So in my lab, we developing new technologies. We call them thermal batteries. So really what we want to do at the end of the day is have a battery that you could turn on and off, where instead of having electricity coming off or in, it would be heat. So such thing doesn't exist at this today. And we believe we could do it, and we're using certain things that I probably cannot speak of right now on camera, but it consists of surface nanoengineering. So we could pattern surfaces, and then we could use what's called liquid metals, and the interaction between the liquid metal and the pattern surfaces allows us to have thermal rectification, whereby we could control the flow of heat in and out of our thermal battery. I run this program called Senegal, and the idea came when I was in grad school. So I went to RPI and I was doing my grad school, and it wasn't the easiest thing ever. And I started to realize that some of the challenges we get as African has to do to the perspective that people have about us. I think when you think of an African anywhere, first thing it comes to mind is he's probably asking for money, or there are diseases in his country, or that stereotype that everybody knows about, right? Whereas it's not the same for an Asian, right? I mean, an Asian who comes, he could be from not in the sciences, but he just needs to wear glasses, and then he's probably way better scientist. He's already a better scientist than an African who's probably top of his class. So there's a stereotype that affects us all in the West. Okay, so I thought that the only way we could solve that problem is to actually go back to the source of the problem, which is Africa itself. We need to have a strong Africa, and the way to make it strong is through our human resources. And one way we could exploit the human resources is education. And we certainly believe that STEM education is at the foremost of this, this drive towards, having a good education in our continent. So I decided to create this organization, and the goal was to promote STEM education through means that are known already to the other countries, such as robotics competition, design competition, and things of that sort. So it has grown since then. I finished my PhD, then did a postdoc, then went to UNL, University of Nebraska-Lincoln, where I'm currently a professor. And during this period, when I was a PhD and a postdoc, I was actually using my own money to run this program. And as a postdoc, a PhD, have really a lot of money. But I was able to manage. But fortunately enough, I went to Nebraska, and I have spoken with my department chair, and I told him about what I'm doing, and I told him that I was using my own funding. I told him, now, can I use some of my research funding, a little bit of it, to run some of these activities? He was very supportive of it. And not only that, he was able to, provide extra funding to run our program. So as a result of that, we've grown a lot. So now we have 3 programs within the organization, within Senegal. We have the most important one, at least the biggest one, is the Pan-African Robotics Competition, which is a competition, it's an all-African robotics competition, which brings together high school, middle school, and university college teams, university teams across the continent to compete on a robotics challenge around a theme that's relevant to the sustainable development of the continent. For example, in 2016, the theme was powering agriculture. How do we use science, engineering, robotics, drones, automation to empower or to have a better agricultural system? This year, the topic was Made in Africa. And the goal was, how do we make the kids or the youth understand the importance of product development, the importance of industrialization, and the importance of innovation. In order to have a continent that's going to rise, we need to not only do service, but we need to produce too. We need to check that market, and we are a producer of products. So this is something very important. And so within those teams, the kids would make they would build the robots, they would make project presentation, and then what they get out of it at the end of the day, besides the technical skill they learn, is the self-esteem, that they know that science they could do it. That the movie that they see, whether it's transformer that is not magic, but it's actually just, basic science and, engineering. And so this helps them actually go forward in their life and believe in themselves. And then we help them also, we try to channel them to go into science as well by this. And beside that, the other benefit of the program is we make science fun, So we're not going into classroom and just, drawing, mechanism or, writing equation. Now they are in a stadium, there are people shouting, screaming, laughing, supporting them, and they are having fun, with this robot, and they mix together, they learn from each other, they learn about their different classmates, they learn about others from other countries, which is very important, especially in the context of Africa, where we need to be really united and work together, So this is the Pan-African Robotics Competition. Along with that, we had created programs that are more or less supporting this whole idea, and one of them is the Azibot Robot Kit. We realized that as we go ahead and promote STEM education, one thing that always comes to mind is, where do we get the kits? Where do we get the robots? Where do we get this equipment to do all this fancy science? So we decided that why can't we build it ourselves? Why can't we actually make this kit and then make it available to them? So we've designed the Azibot Robot Kit, which is a robot. This has the same state-of-the-art technology as any other robot that you would find in the market. And we've made the robot open source. That means all the equipment, all the materials, the knowledge that's needed to make the robot is available online. It's 3D printable. The electronics are also open source. So this is pretty much our organization, and we keep growing. The past 2 years we were in Senegal. This year we are in Rwanda. In 2018 rather, we will be in Rwanda for the Pan-African Robotics Competition. We expect to have over 20 countries across the continent. Beside our work we do with the Pan-African Robotics Competition and the various robot kits that we're developing, we also recently opened a university called Dakar American University of Science and Technology. We believe that we were doing fine with working with these kids and inspiring them, but it turns out it wasn't enough. We need to actually follow up with the students, and following up we need to keep them with the same high standard of learning and innovation. So we decided to open this university to provide those services. A lot of schools, a lot of universities in Africa, which I do not know all of them, but many of them do not emphasize practical science. You learn a lot of theory, you're really good at math and physics, but if you are given, a simple problem as far as, fixing something, it becomes a problem, and we don't need to name examples, but we've seen in more than one cases where our countries have, really basic, small problems, and we outsource them to the West. So that means our engineers are not being trained the right way, and this is not just a general statement, not necessarily true to all cases. So the purpose then of our university is to fill that gap, which is to provide high standard, practical hands-on engineering to our African students. So we started in January 2017 and had a couple of students. Right now we're starting the fall of 2017 we expect to have about 60 students. And our students live on campus, they eat on campus, and the campus is located in a city called Somone in Senegal. What I'm more interested in is really how the knowledge that I've acquired, how this program that we've started will impact, the African community, really. So all the work that we've been doing, do we see the result? Are we getting engineers that are very strong fundamentally, but also have very practical skills and that are commercial? They are marketable. They could go out in the market and get jobs. I think that's really what I would be very satisfied or very fulfilled if we were able to achieve this. And of course, the ultimate goal is not to get engineering scientists, but also engineering scientists who could solve the societal needs of Africa, so we don't have this problem anymore. I want to be able to go to the West, and people will see me and think I'm a quantum physicist. If I'm not, but just because there's so many quantum physicists in Africa, or because we've been doing so great, we've been inventing things. Everybody thinks that I'm smart, and not look at me as just another guy who just took the ocean and is migrated to Europe.